We have everything set up to train our link prediction model, and that's what we'll do next. I've set up a train function which performs the model training. Within the train function, I switch the model to training mode by calling model train, and I zero out the optimizer gradients. I then generate the embeddings for each node by calling model encode and passing in the node features and the connections in the graph. If you remember, when we generated our training data using random link split, we asked for the training data to not contain any negative edge samples. That is, pairs of nodes which are not connected by an edge. Here are explicitly generated the negative samples for training in every epoch. This is the code on lines 11 through 13. I use the negative sampling function. This function takes in the current graph structure, that is the number of edges in the graph and the number of nodes in the graph, edge index and num nodes, and the number of negative samples that you want to generate. I basically set the number of negative samples to be equal to the number of positive edges that we already have in the training data. By performing negative sampling for every training epoch, we generate a different set of negative samples for each epoch. The shape of negative edge index is given on line 8. It's 2 by num training edges because we are generating as many negative edges as we have positive edges in the data. Next, on lines 16 through 19, I set up an edge label index by concatenating the current edge label index with the negative edge index. This concatenation allows us to put together the negative and positive edges in our training data. The shape of this edge label index that we form by concatenating positive edges and negative edges is 2 by num training edges multiplied by 2. This edge label index is what we are going to be using to train our link prediction model. Now we have to set up the corresponding edge labels corresponding to the edge label index. That is, for every connection we have to specify whether it's a positive edge or a negative edge. This is the edge label which I formed by concatenating the trained data edge label. This is what represents the positive edges, and then a tensor of all zeros equal to the negative edges in our training data. We have the encoded node embeddings in the variable z. I call model decode passing in z and the edge label index, which has both the positive as well as negative edges. Out contains the unnormalized predictions of the model, and then we use the loss criterion to compare the predictions of the model with the actual ground truth labels, edge label, loss, backward computes gradients and optimizer, step updates the model parameters, and we return the loss from the train function. I'm going to set up another function here, the test function, that will allow us to perform link prediction on the test data. The test function takes in the data as an input argument. I've also applied the PyTorch node grad annotation to ensure that gradients are not computed. When we make predictions on the validation or test data, we switch the model to evil mode, model, evil. We call model encode to get the node embedding representations. We call model decode and invoke the sigmoid function on the result to get normalized probability scores in the adjacency matrix that is generated by the decoder model. We then compare this generated matrix out with the edge label in the actual data, and we compute the Rousey AUC score. The AUC, or area under the curve, is a performance metric for binary classification models representing the area under the receiver operating characteristic, or ROC curve. The ROC curve plots the true positive rate against the false positive rate at various threshold settings. A higher AUC value indicates better model performance. AUC thus evaluates the discriminative ability of a model. Now that we have set up our training function and test function, here is the code to train our link prediction autoencoder model. I initialize the best validation accuracy and the final test accuracy to 0. We'll train for 100 epochs. That's what my for loop is set up for. I call the train function, which will run training for 1 epoch, and I compute the loss, and then I compute the validation AUC and the test AUC on the validation data and the test data. If the validation AUC computed is better than the best validation AUC that we've seen so far, we store the best validation AUC and the final test AUC in the respective variables. And after every 10 epochs of training, we print out the epoch, the loss, the validation AUC, and the test AUC. And I also print out the final test AUC. Let's run training on our model. It should run through fairly quickly, and you can see the final test AUC is 0.8989. AUC close to 1 indicates a good classifier with good discriminative ability. So our link prediction model seems to be fairly decent. Now that we have a trained model, let's actually use it for link prediction. I call model, encode on the test data and passing the nodes and the edge indices of the test data. And this will give me the embedding representation for every node in the test data set. Remember, The test data is made up of all of the nodes in the original graph and a subset of the edges. If you look at Z shape, you should have an embedding representation for every node in the graph. There are a total of 3,327 nodes in the graph, and each node is represented using a 64-dimension vector. Let's get the adjacency matrix with the link predictions for all edges in the graph. I call model and pass in the embedding representations of all nodes. And this gives us final edge index. If you remember the code and decode all, it only identifies positive edges where the probability of an edge being present is greater than 99%. And you can see that it has identified a total of 4,594 edges in our graph. In our autoencoder model, the decoder uses the inner product to compute how similar two nodes are in order to predict whether an edge exists between those two nodes. This means that every node is likely to be connected to itself because a node is very similar to itself. These are self loops. Let's go ahead and get rid of the self loops that exist in our adjacency matrix. We know that the original graph did not contain any self loops. So on line 1, I have the condition for a self loop where the source and the target edge are the same. And on line 3, I perform a simple filtering operation to get rid of all of the self loops in the adjacency matrix predicted by the decoder. And I'm left with 4,502 edges. Now, how many edges did the original graph have in the test data? Let's look at the edge index shape here, and you can see that there are 7,284 edges that were present, and only a fraction of those edges were predicted as positive edges by our model. That's because we were very conservative in identifying edges and decode all. We only identified those edges of we were very certain, that is, edges with the probability of greater than 99% based on our model.